All right, so we are on our last day of content for this unit and for the course, and after this, it'll just be our culminating and exam, and we will be finished with grade 10 math. So the last two things that we are going to look at today are two specific types of applications of quadratic functions. So we already looked at objects flying through the air yesterday, and now we're going to look at two other specific types of applications. And the first one is area and perimeter problems. So I think it's easiest if I just hop in with some examples rather than giving steps. You can see how we set these up. So the first question here says, Timothy wants to create a rectangular dog park at the neighborhood park. If he wants to use exactly 600 meters of fencing and one side of the park will be beside a pond, what dimensions maximize the area of the dog park? Okay, so first I'm gonna just draw like a picture so we can see what's happening here. So we wanna have a fenced in area. However, it's only fenced in on three sides. Okay, so we would have something like this. And because the one side is beside the pond, I guess we're not putting a fence there. So we'd have water here. So we're only fencing three of the sides. Okay, so if we have our diagram here, typically in a rectangle, we would label this as length and this as width. Okay, so we would have two widths and one length. And we want to take a look at what is given to us in the question in order to be able to solve. So it says that he wants to be able to use exactly 600 meters of fencing. Okay, so if we picture what the fencing is going to be and what that represents of this rectangle, that is going to be the perimeter. Okay, so if we make an equation for perimeter, we could say that it is equal to 2w plus the length. Okay, because we have two identical widths and only one length. And we can let the perimeter equal 600 because that's how much fencing we want to use. Okay, so we can have this equation instead. 600 equals 2w plus the length. And what we want to do then is we want to be able to rearrange this equation so that we have one of the variables isolated because we're going to substitute it into another equation later. So this might remind you a little bit of the linear systems equations where we have one equation that we use substitution for into another equation. So in this case, because I already have L with a coefficient of 1, what I'm going to do is I'm going to just bring the 2w over to the other side by subtracting, and then I'm just going to reorder this. So I can say then that L is equal to 600 minus 2w. Okay, and I'm just going to call that equation 1. So that is all just derived from the perimeter equation, right? I was given the amount of fencing. I can, with variables, write an expression for perimeter, and then I'm just isolating for one of the variables. You could also isolate for w if you wanted to, but you'd have some division involved there, so it's just less messy to isolate for L. So now we want to maximize the area of the dog park. So we know that area of a rectangle is given by length times width. So what we are going to do is we are going to, if we call this equation 2, we're going to sub equation 1 into equation 2, or you could just write like sub L into this equation. Okay, so we can't maximize or do anything to solve until we only have one variable that's unknown. Okay, so we're going to have A is equal to, instead of L, we are going to write 600 minus 2w, and that's being multiplied by w. Now you may be tempted to expand this, and I understand why. I always want to expand these as well, but don't, because it will just make more work for yourself. So we want to maximize the area, meaning that we want to find the vertex of this quadratic. Okay, so if we were to expand this, we would have like right, we would multiply this here, we'd have 600w minus 2w squared, so we would have a quadratic equation. But we know that one of the ways we can find the vertex if we are in factored form is from the axis of symmetry. Okay, so this form isn't fully factored, like we could still divide both of these terms by 2, but that doesn't really make a difference in this case. So what we want to do is we are going to let a equal 0, because that's what we do when we are maximizing something, right? When we're finding the vertex, we have 0 equals 600 minus 2w times w, and now we're going to let each bracket equal 0 and solve. Okay, so one of these here, we've got, this is just w equals 0, and then we'd have 600 minus 2w equals 0, so 600, if we bring the 2w over, it's going to be positive. We'll divide by 2 on both sides, so we'll have 300 is equal to w. Now be careful here, this is not telling me that the width is 300. Okay, because I also have this one. So these are like my two, they're not necessarily the x-intercepts of the function, because this is not the fully factored form, but what they are, like it's, we can use these two values to find the axis of symmetry. Okay, so if we do that, axis of symmetry, we'll have w equals 300 plus 0, which you don't really need to show, over 2. Okay, so the width is going to be equal to 150. Okay, so that's our first measurement that we're given. So make sure you do the axis of symmetry part before you find that, right? Because we need to find the maximum. So this is telling us when w, or when the width is 150, that's when the area is maximized, is the biggest it can be. So then we will go and sub w equals 150 into equation 1 to figure out what the length is going to be. So length is equal to 600 minus 2 times 150, okay, which is 600 minus 300. So the length is going to be 300 meters. This one was also meters. Okay, and those are what the dimensions are to maximize the area. Okay, so I ran out of room here, but you would want to write the therefore statement. So we'd have therefore the dimensions are, and then just write them out, and make sure you include the units. So yep, that's how we do that. Okay, so if you're given information about the perimeter in the question, you'll set up an equation involving the perimeter and isolate for one of your variables. Then we are looking at area, so we'll set up an area equation, sub in our rearranged first equation so that we are only working with one variable, and then we can solve, right? Typically these are going to be maximizing, so you'll want to find the axis of symmetry like that and sub it in. And the nice thing that you can use just to check this, don't use this as your method, otherwise you will not get full marks, is that you notice here the relationship between the width and the length is that the width is half of the length, okay, or in other words, the length is twice the width, and that's always going to be the case, okay? So that's a nice little check for yourself when you are working with a three-sided shape like this, like a rectangle that's open on one end. The length will always be double the width, so that's something you can use to check your answer, but you cannot use it to solve your question, okay? Even though I know it's tempting to, you need to make sure that you're showing this work, okay? So that's one example of an area application. If we take a look at this next one here, this says the length of a rectangle is 16 meters greater than its width, and its area is 35 meters squared. So we want to find the dimensions of the rectangle. Okay, so the difference here is that we are given a few things. So we know, okay, the length, that is not my highlighter, one sec. The length is 16 meters greater than its width, and the area is 35 meters squared. Okay, so we're going to set up two equations again. The first one we can set up, we know, maybe the easiest one to set up is the area. So we know that area is equal to length times width, and in this case we know that that's 35, so we can have 35 is equal to length times width, and that would be our first equation. And the second piece of information that we're given is that the length is 16 meters bigger or greater than its width. So we could say then that the length is equal to the width plus 16. Okay, so that's representing length is 16 meters greater than width. Okay, and we can call that equation 2. So we're going to sub equation 2 into equation 1. All right, so we would have 35 is equal to width plus 16 times width, right? That's our length times width. And in this case, we're trying to find the dimensions, so we want to solve for W. So we need to expand on the right side and then bring the 35 over. Okay, so first I'm going to expand, so I'm multiplying both pieces of the first bracket by the second bracket, so I'll have 35 equals W squared plus 16W, and then I'm going to bring this 35 over. Okay, so I'll have 0 equals W squared plus 16W minus 35. Okay, and then now I want to see, I should first check if I can factor. Okay, so this is a simple trinomial because there's no number in front of my W squared term. So I want to find see if I can find two numbers that multiply to negative 35 and add to 16. So 35, the first, okay, so we could have 1 and 35. 2 is not going to work nicely. 3 does not work nicely, neither does 4. We could have 5 and 7, and that's it, right? Because 6 doesn't work, and then we're just back at 7. So if we were to look at this, the last number is negative, so one of these needs to be negative. But in looking at this, none of these options are going to add to give me 16, so that's telling me this is not factorable. Okay, so I'm going to just erase this here. It's not factorable. I tried, because if it was, then it would be a lot easier. Okay, so we are unable to factor. So I'm going to go up over here and do my quadratic formula. Okay, so A is 1. B is 16, C is negative 35, and then now I'm just going to use my quadratic formula to solve. We always write x, but in this case you technically should write w, because that's the variable that we're solving for. Equal to negative b, so negative 16 plus or minus the square root of 16 squared minus 4 times 1 times negative 35, all divided by 2 times 1. Okay, so if I simplify this, inside my square root, 16 squared is 256 minus 4 times 1 times negative 35. I get 396 under the square root. And then this is just divided by 2. Okay, so if I look at my two options, sorry, I'm not showing all of my steps here just because I'm trying to save room. This gives me 1.95, and this one, if I look at the other one just to double check, I'm assuming that the other one's going to be negative, but I'll check it just to make sure. Divided by 2, this gives me negative 17.95, which obviously is not going to be an option. Okay, so we would say that this one is inadmissible because it's negative, right? We can't have a negative width. So this one is going to be the right one. The width is going to be approximately 1.95. Okay, this tells us to round to the nearest hundredth of a meter, which is 2 decimal places. Okay, so that is the width, and then I need to sub W into my second equation to find the length. Okay, so then I'll have length is equal to 1.95 plus 16, so my length is equal to 17.95, which oddly enough, it's not odd actually, it's not a coincidence, this is how it usually works, is that this 17.95 is the same number that we got here, it's just not negative. Okay, so then those are my dimensions, so I would just use a sentence answer, so therefore the dimensions of the rectangle are 1.95 meters by 17.95 meters. Okay, so the application problems that you'll see that are similar to this will always kind of follow the same form. So sometimes you'll be given information to set up a perimeter equation, and then you can substitute it into an area equation. And in this case, we weren't given any information about the area other than we were trying to maximize it. So that's why we let it equal 0, and then we're solving that way. Whereas in this case, we are given no information about the perimeter, but we are given information about how the two measurements relate to each other, as well as the actual area. So we were able to set up equations that way. Okay, so each one will be a little bit different when you set it up, but like the variety of them is like there's not a huge variety of them, right? Once you've done a few questions, you will kind of know how to solve any type of question like this. So the key thing to remember is that you always want to set up two equations, so similar to with our linear systems unit, and you want to make sure that you have one of them in terms of just like one variable, like you have one variable isolated like we had here for L, and in the previous one we had L isolated as well, so that you can use substitution, and then you're just asking yourself, what are you trying to find? Okay, so if you're maximizing, you obviously want to find the vertex, whereas if you are just finding the dimensions, that's solving for W, so that's what we did in this case. You would factor if you can, or use a quadratic formula. Okay, so make sure you do some practice questions like this because they are pretty easy once you get the hang of it. Like I said, the variety of them is pretty small. So if you do the practice questions that I provided, then you will be set and should be confident to be able to do these questions on the test as well as on the exam.